can give this to the other people who couldn't come. Eric, you can just introduce yourself because I basically Googled your website and then copy pasted your nice paragraph. So I think you can probably explain it better. But yeah, Eric.
Yeah, no, thank you so much for having me. So I'll actually, can I just, the beginning I had a little bit of a, so could I share my screen actually and just
Yep.
jump into it then? Great. Let's do here and then, okay. Yeah, well, hello everyone. Really nice to meet you all. It sounds like there's a lot of cool human robot interaction work that you all are working on. So I have a lot of my own questions I'd love to ask you about, but I'm really happy to be here. So yeah, my name is Eric Rosen. I'm a third-year PhD student at Brown University, advised by Stephanie Telix and George Konadaris. And based, as you can see on the title of the talk, what I'm going to be coming here and talking about today is a little perspective that I've been having myself, which is about how to expand the robot toolkit with mixed reality. And so Tom actually reached out to me and I've talked to him a little about this idea. And so I think he was interested in me kind of sharing some of these perspectives and talking about my own research. So I'm really glad to be here. So a little background on myself, my research goal or interest is in developing algorithms, systems, and interfaces for intelligent collaborative robots. And to this end, I mostly work at the intersection of three kind of fields: reinforcement learning, virtual, augmented, and mixed reality, and human-robot interaction. And so, as you kind of tell based on the talk today, what I'll be mostly focusing on is on this mixed reality at the intersection of human-robot interaction, but I'll also be talking about later at the end some of the work that I've done with integrating reinforcement learning into this. And if you have other interest about the work that I've done, and more recently, I'd be happy to talk about that as well. And one thing that I really want to put at the forefront of what this talk is going to be about is really, I'm hoping to share with you all some new tools and perspectives that you may not have had before. I'll be describing the high-level inputs and outputs of the systems that I've developed and show off a lot of cool demo videos to hopefully get your mind thinking about what can be done with this kind of technology. So hopefully this will make it more readily accessible for those who are maybe not as familiar with this kind of technology. Rest assured that behind the scenes, there's plenty of complex mathematical formulations, lots of details on system architectures, and lots of graphs and charts that if you want to know about, feel free to ask. I love getting into the details of things. But what I'll emphasize is that if anything seems too high level or if you're confused, I really hope that you guys can all just jump in and ask questions. Maybe, I don't know how we want to facilitate this with raising hands, or if you just want to unmute and ask. But throughout my talk, I have a lot of natural points where I'll have a takeaway, I'll take a sip from my water, and if anyone wants to maybe jump in and ask a question, then that's a very natural point to do that. So as an overview, what I'm going to be talking about is what is the robot toolkit, what's in it. Then I'll talk about what is VAM-HRI and what those technologies are. I'll talk about what I mean by what I call the mixed reality robot middleware, which is really what you need in order to start using this kind of technology and get it working in your own projects. And then to get your mind spinning, I'll start actually showing some examples of research I've done in VAM-HRI, specifically for robot control. So let's talk about what is the robot toolkit. When I think about the robot toolkit, I think about what do I as a roboticist have available to me today? And I feel very fortunate because I think we're kind of in a great point of time. I mean, if you look at the history, when you go back into the 1950s, when they were just making the first industrial robots, there really was no intelligence to them. You really couldn't do anything outside of program very specific motions. And over time, we started building more intelligent robots that had a little more autonomy and let us do a little more with them. We could do more fun things. But at this point, you still had to build your own robot, which I have a huge amount of respect for. And so it's really nice that kind of towards the 2000s, we start seeing companies like Willow Garage actually developing robot hardware for us to use as roboticists. And then what that's really led to now today in 2021 is what you can do is you can just buy a research robot platform and actually get a lot of cool software right out of the box with it. And that's what I think about as the robot toolkit. So for those who are familiar with robotics, really know that when you get a robot and you get something like raw set up on it, there's so many cool packages that come out of the box, right? I mean, I could start doing motion planning with my robot. I can start doing some basic perception with fiducial markers. If I have a pretty static environment, SLAM is really out of the box and I can make nice maps and localize. If I want to connect with humans, I can do some speech recognition. I can visualize a bunch of my information, control my robot. I can even do skeleton tracking with RGB data. The really nice thing here is that the robot toolkit is comprised of a lot of things from like computer vision, natural language processing, and control theory, and packaged very nicely for us to use right out of box on our robot. So if you're already familiar with kind of the robot middleware and ROS, these kind of things are just right at the tips of your fingers. And to think about how important these are in actually improving your projects, to not know about one of these technologies would probably could be very difficult to do certain things. So knowing about what is at your fingertips is a very important thing as a roboticist. And so what I'm really hoping to communicate to all of you today is that mixed reality technology is available and it's ready to be used, and you can put it into your own project. So I think it's a really cool thing, and that's really what I want to communicate here today. So I mentioned mixed reality, virtual reality, augmented reality, but what is that technology? And I'm going to just say right off the bat, these terms are really confusing because there's a lot of marketing going into this. There are huge companies trying to sell these technologies, and so they're going to use these words in their own way to try to product price, make them more attractive and differentiate from the competition. So the general kind of thing that we use to differentiate these terms, I'm going to say there's virtual reality, and you may be familiar with this with like the HTC Vive or the Facebook's Oculus Quest. What you're seeing here is this head-mounted display that has a screen on it that you'll look at so that you can see a 3D environment. You'll see these hand controllers that are actually positionally tracked so that as you move them, you can see them in the virtual environment. And the only difference between the Vive and the Quest here is that the Vive has these little boxes around it, and these are called lighthouses so that they can actually track the headset and the hand controllers. We call this outside-in tracking, whereas the Oculus actually has cameras on it and is localizing and making a map locally. We call that inside-out tracking. But the important thing here is that we're looking at a screen. And so to give you kind of an understanding, if you want like a reasonable headset, you can probably spend around $300 to $1,000 and buy something like this, commercially available today. On the other side, augmented reality doesn't have you look at a screen, but actually augments the reality around you. So this is something like Google Glasses or HoloLens, which look more like actual glasses because you're actually looking at the real world. And what's happening, as you can see on the Google Glasses, there's this little LED light that's actually being used to project light onto the glass so that you actually see an augmented version of the real world. And the HoloLens is similar. This technology is running a little more expensive nowadays, from like $1,000 to $5,000. But once again, another commercially available technology for you to have. So that's kind of the words here, virtual reality and augmented reality. How does that relate to human-robot interaction? And when I think about this, I generally think about this mixed reality spectrum. So I'm going to use the word mixed reality as a very catch-all term for augmented reality and virtual reality. And the important thing is we have this diagram that goes from the real world to the virtual world. And if we look at the virtual world first, you can probably imagine virtual reality sits there. It's really good for when we want to work with virtual worlds. So here you're actually seeing a video of something we call Robot World, which is kind of a pun off Elmo's World, where we have a bunch of robots that are various robots that are just dancing around that you can see, a very synthetic and fake world that's fun. Great application of virtual reality. And in general, when I think about what virtual reality is used for in human-robot interaction, I think about remote human-robot interaction. So when the human and the robot are not together, then I think about using virtual reality technology. On the other end, we have augmented reality, which is more situated for the real world. So for here, what you're seeing a video of is actually a human wearing a HoloLens, and the robot is making these motion plans about how it wants to move its arm, and it can actually visualize that directly into the real environment. So this is really useful in the case of in-person human-robot interaction, because if the robot and the human are situated together, we don't want the human to look at a screen. We want them to look at the real world. So augmented reality is very powerful in that context. So did not mean for those videos. I don't know why those videos popped over it, but the takeaway here is that mixed reality is a catch-all term for virtual reality and augmented reality, and virtual reality is mostly for human-robot interaction, augmented reality for in-person human-robot interaction. Apologize for these videos overlaying, but I'll stop here as just kind of the first takeaway. So if anyone has any questions about what these technologies are or any questions, feel free to jump in or ask. Okay, great. So let's continue on. So one thing that you'll notice is that in general with these mixed reality technologies, they actually leverage a lot of the similar things that exist in the robot toolkit that I mentioned before. So here's a demonstration of the HoloLens 2 being used. And what you're noticing is that that headset is tracking their hand gestures so that they can interface with this little slider. It's tracking the position of the person and making a map of the environment so as to keep things stable. You can't hear the audio here, but there's actually some speech recognition going on. A lot of the things that are in the robot toolkit are actually have a lot of overlap between what the mixed reality headsets themselves need to do. And so this is really interesting because I think about mixed reality technologies and robotics as very overlapping areas of research. And from a perception capability, this is not my own viewpoint. This is actually, if you're interested in this kind of overlap from a perception point of view, I highly recommend this paper by Andrew Davison on future mapping. And the really important thing here is that he emphasizes and makes a lot of points about how the spatial perception capabilities of a robot are going to be very similar to the spatial perception capabilities of a mixed reality headset. And so there's a lot of overlap that we can be doing here and things that can really be synergized. So really a big takeaway here is that there's a lot of overlap between the perception capabilities of a robot and a mixed reality device. And so it almost acts as a second robot, but with very little actuation capability in its own right. So that's also a very nice insight. I'll take another second here if anyone wants to jump in or ask any questions. So I started off saying I'm interested in reinforcement learning. So that's all about actions and controls and making decisions. So I'm going to be talking a lot about how my own research in using mixed reality, not necessarily just for purely perception capabilities, but for controlling and working with robots. So now the last two things I'm going to talk about in this talk is mixed reality robot middleware. How do you actually, this technology sounds cool, you like it. How do you actually get started with it? So I'm going to talk a little about that. And then I'll emphasize some examples that I've been doing for VMHRI in robot control. And so there's a lot of ways you can use the technology, but to maybe give you a working example, what I'm going to start with is introduce this low-level mixed reality robot middleware, which once you have it introduced, there's so much you can do. And to give an example of that, I'm going to go through what I call this kind of control autonomy hierarchy, where essentially there's low-level control of a robot in the form of something like teleoperation. There's more mid-level control like visual programming, and maybe high-level control in the form of I want the robot to do multimodal intent inference. And so I'm going to go through today various ways that mixed reality can be integrated into each part of this hierarchy. But before we can do that, we need to get the mixed reality technology into our robot toolkit. And that's what the mixed reality robot middleware does for that. And so one example of that is ROS Reality, which is a system that me and a fellow PhD student had wrote a couple of years ago, which was one of the first toolkits for actually connecting mixed reality technology to existing robot middleware like ROS. And this is a very fancy system diagram that if you want the specifics on, I'm happy to talk about, but let's abstract it away and just think about the high level what's happening here. What we have is we have a robot, and that robot is ROSified. We also have this mixed reality headset, whether it's a virtual reality headset or an augmented reality one. And we need a way to develop virtual environments with it. And so the most common thing today to use is the game engine called Unity. And this is a very powerful physics engine and gives us really good rendering and visualization capabilities for developing scenes with this mixed reality technology. And really what we need to do is somehow connect Unity to ROS so that we can actually have these technologies communicate. We want sensory information from the robot to go to the mixed reality technology, and we want that MR tech to communicate with the robot. So here's a very, very high level diagram of that, where essentially what happens is there's the robot and the user, and they share this virtual space. And whether this is remote or in person, the point is that what we can do is communicate sensor information from the robot to that virtual world. The human can see that and interface with it and send controls back to the robot. And so if you really want to get into this, I don't really recommend using ROS Reality anymore. It's a little outdated, but there's this amazing one called ROS Sharp that I know Tom can attest to. And it's a really great library that is right out of the box. You can Google it. It's right here. You can just go to their GitHub page. And what it'll do is you just install Unity on Windows. You get your ROS going on your computer. And there's a lot of cool things you can start doing, like actually transporting URDFs into Unity, communicating sensor information, topic information, a lot of cool stuff, everything that you probably really want. And so a real big takeaway I guess I want here is that if this is of interest to you, one thing you should start doing is playing with Unity. It's really cool and a great game engine. And check out ROS Sharp. It's very easy to connect your ROS network to a Unity setting. And if you have your virtual reality or augmented reality headset of choice, very easy to connect in. So I'll stop here again. And if anyone has questions, please feel free to jump in. Great. Okay. So that's the basic middleware, and I've told you where you can go to find it and how to get into it. So let's start seeing some cool examples of this stuff, right? So at the simplest thing, what I want to do is maybe control the robot on where its end effector is going to go. This is pretty important because teleoperation has a lot of good applications in terms of remote control. And so here's an example of us actually using ROS Reality to teleoperate a robot to fold a t-shirt. And what you're seeing is there's in the 3D world that you're seeing is a rendering of the RGBD depth image from a Connect on the robot being turned into a high fidelity point cloud. And along with that, the robot has these eye-in-hand cameras on its wrist. And those are actually being displayed as little squares next to the controller to the human to give another sensing modality. And what happens is as the human moves their hand controllers, the robot is moving accordingly. And as the human moves their headset, they get a different perspective in the scene. And so this creates an extremely natural interface for controlling a robot to do a relatively complicated task like manipulate a deformable object. And so this is just one demonstration of how you can do low-level teleoperation with this. And so you're seeing the human and the robot right next to each other, but I emphasize that virtual reality is for remote interactions. So just to emphasize this exact same technology, we actually did it from Brown to MIT. So this is over 40 miles away. And rather than doing this shirt folding task, we have this cup stacking task. And so what you're going to see here is I'm just using ROS Reality to teleoperate the robot. And so this is a relatively difficult task because you actually have a lot of contact forces happening with cups. And so it's really cool to see that with really commercially available hardware that you can just buy today and relatively simple setup, you can get this going on your robot very quickly. And it's really effective. So just to demonstrate, and I guess I'll just jump to the end of the video here, but we can stack all these cups pretty reliably. And it doesn't have to be with just an expert. So I want to emphasize, I'm not going to get too much into the user studies that we ran here. I'll just try to keep this at a very high level. So from a perspective of teleoperation, you have a controller and a display. And really the canonical way that you would do something like teleoperation is maybe with a keyboard controller and a 2D monitor display. And what we wanted to investigate is how much better a virtual reality controller that's positionally tracked and a virtual reality headset provided you in terms of how fast you could do these manipulation tasks and how much cognitive workload the human had here, where I'm kind of using arrows down to be bad and green arrows upwards to be good. And to kind of just further disambiguate this, because there's a controller and display, we investigated whether if you had this kind of hand controller from virtual reality, but you were still looking at a 2D monitor. And it's a little difficult to do a keyboard and a headset because you can't see your hands in virtual reality, so it doesn't really make sense. And what we, as you could probably infer, we found that virtual reality was really good, but actually just having the hand controller was really helpful. And the monitor itself didn't really make too much of a difference. So this is all just trying to say here that this mixed reality technology for teleoperation can be a very powerful interface for low-level robot control. And I already emphasized technology for VR and mixed reality is very similar. And so this doesn't just have to be with virtual reality. So if we want to do in-person interaction, what you're seeing here is a human wearing a HoloLens and pretty much using the same exact ROS Reality setup. What we can do is visualize it into the real environment. So here a human is dragging red and green end effectors for where they want to program the robot to move. And then the robot can actually make a motion plan for how they want to move to that end effector, and it can actually visualize its entire plan of getting there. So this really makes the intent, the motion intent of the robot extremely clear to the human. And this is very, very important for safety reasons and in-person interactions. So this is another way of doing very good low-level control on the augmented reality side of things. So cool, we have a lot of cool teleoperation capabilities that come out of the box with this. So, but that's a little cumbersome to be specifying all that low-level information. Maybe we want to actually make it a little easier for the human to specify some higher level information, maybe even program the robot in a way that we normally think about. And that's really where visual programming comes in. So rather than just programming where you want an end effector to be, maybe we should actually write code that can actually have conditional statements, some looping, and actually be able to program how we want waypoints to be adapted. So here what you're seeing is a mixed reality interface where a user can essentially add in waypoints, add in some conditional blocks that they want, and then even save their code and adapt it for new situations. And there's even some perception capabilities where if we know where a block is and a person puts a gripper close enough to a block, then we can autonomously have the robot correct for that and grab the block if the end effector isn't perfectly above it due to decalibration issues. And so this is a really immersive and effective, slightly higher level way of programming the robot to do a task. And as you can imagine, this kind of mixed reality method was much better than operating on a keyboard and a monitor where you were looking at the real world through maybe an RGB image. So that's all really nice. But there's even more information that we can give because there's a lot of important information that you may want to specify for a mobile manipulator, for example. So what about object information? So objects have kinematics, which define the geometries of their motion. That's pretty important. You might want to be able to specify to a robot where objects are, or how to grab them, or how to even manipulate an object so that once you know how to manipulate one object, it can generalize that information. So we really want to investigate how far we could push this building a plannable representation with mixed reality. And that's what you're seeing in this demonstration, where what we did was we could specify a whole slew of information about objects relevant for task and motion planning and have the robot actually do that. And here you're actually seeing a human in the loop continually correct information about the robot until it can get it correct in a learning process so that it can then perform those in more novel situations. So this is a really showing that there's a lot of middle level information that can be used to supply with mixed reality. So in this case, what we can use to mixed reality is that we can specify things like the kinematics of an object, where objects are, how to grab them, manipulation policies on those objects, and semantic attribute information. And this information can be defined locally so that it can be reused across objects in the environment. So this gives the user a little higher level control over how they want to interface with the robot. So I'll stop here if anyone has any questions about this kind of mid-level control. Yeah. Okay, great. So let's get into the high-level control.
Oh, Eric, I think Lauren has a question.
Oh, I'm sorry. Yeah, I don't have the chat open, so I apologize.
Yeah. No,
oh, no, it's okay. I just unmuted myself, but that's okay. So is the intent that you're discussing that if the person puts the end effector near an object, but kind of like maybe incorrectly, like, or not close enough to the object, it just kind of assumes what they're trying to do?
Yes, in a very simple way, that is a basic heuristic of like, I know I can perceive where I think the object is, and here is where that poses. And if it's within a certain distance, I'll just grab onto it. So that's a very simple kind of, I'm not even gonna refer to that. I guess that is a kind of intent, yes, but we're not really even having the robot model the intent in an intelligent way. So that's what I was into this last work, which is actually
okay, cool.
Which is much more interesting in my mind. But though this is very powerful from a mid-level program. But yeah, great question. Great. Yeah, any other questions that people have? Cool. Yeah, so let's talk about that high-level control, right? Because all these cases, the human is using what I would argue is maybe not the most natural way that we communicate with each other, right? We're doing a lot of still what feels like programming. So what multimodal intent inference is about having the fact that the human has some hidden intent that they want to communicate to the robot. And multimodal is referring to the fact that they may use various different channels to express that information. And it's a giant field. So let me just give a specific example that we worked in. So here's a human and a robot, and there's a bunch of objects on the table. And the human has an object they want in mind. So they have this marker on the right that they want the robot to hand them. So multimodal, they can use gestures and language. So they might say, can I have that marker? And they'll point at the marker. Now, what the robot does is it's taking in this input, which is a stream of noisy human language and gestures. And the robot's goal is to quickly pick up the intended object that the human has in mind. But the issue here that makes it really hard is that noisy side of things, right? I mean, from a language perspective, the human wants the marker, but the speech tech messes up and hears dark bird instead of marker. And that yellow thing on the left is a bird. And so, language is being a little confusing there. And also there's a connect that's on top of the robot that's very far away from the human potentially. And so it's getting noisy gesture pointings. And so like the gesture is not aligning with the language in any way that really makes sense. This is confusing. How would the robot be expected to pick up the intended object, let alone quickly, right? So to resolve this ambiguity, we'd like to endow the robot with the ability to ask questions. So maybe it can point to an object and say, do you want this one? And if the human can then maybe give some intelligent feedback by saying, no, the other marker, the robot should hopefully intelligently resolve this and understand that the human wants the right marker and choose it. So this is a difficult problem because we don't want the robot to ask too many questions. That's cumbersome, but we want it to be accurate, which requires asking questions. So the way that we got around this is that we actually model this problem as a partially observable Markov decision process, which we call the fetch POMDP, the feedback to collaborative handoff POMDP. And I won't get into the mathematics of it. You can see our graphical model without any labels, which makes it very difficult to understand on the right, but I'd be happy to explain it more. The important thing here is we're actually going to maintain a belief distribution over what we think the human wants. So here at the beginning of the interaction, we have a uniform belief distribution over things. The human says, can I have the marker? That makes us more likely to think about the marker because they're pointing and they have a language, and we have an observation model about these sensing channels. The robot can then use a planner to actually then make a decision that maybe asking a question will help resolve its ambiguity. The human says, no, not that one. And the robot becomes more sure about the other item. And so actually modeling the human's latent state using a probability distribution allows us to quantify our uncertainty and make intelligent decision behaviors. So to just kind of emphasize how important doing this intelligent question asking is, there's kind of three basic setups we had, where in one case, the robot asks no questions and is just going to kind of pick an item when it's very sure of it. So in an unambiguous situation, that's very fast, but it's very inaccurate because it can't resolve its ambiguity. Another thing is to ask lots of questions, maybe to go down the line and keep asking questions until you get a yes. So that makes you really slow and annoying, but you become very accurate because you always at least ask about what you need and be sure of it. And then there's our intelligent question asking method with the fetch POMDP, which can be fast when the situation is unambiguous and it just won't ask questions intelligently. And when it is ambiguous, it will ask questions and still be accurate. And all this is completely autonomous, which is really nice. We don't have to say what's an ambiguous or what's an unambiguous situation. Through just defining the POMDP, it all falls out very nicely. So maybe a takeaway from this is that robots can model humans' intent from noisy multimodal observations, and that allows us to ask intelligent questions. Cool, that's a really cool project. I like it. But how does that connect to mixed reality? So if we look at a high level, actually, sorry, I'll stop here. Does anyone have any questions about this model before I move on? Okay, great. So let's think about what's going on here. The human is using speech and gestures to communicate to the robot, and the robot's using physical pointing gestures and language to communicate back to the human. So what we can do is what we found is what happens if we add mixed reality into this project? How can it enhance this? And there's at least two ways that become immediately obvious. First, we get a new channel to observe from, which is eye gaze, because the headset is actually just situated on the head, and we can now track their eyes. And actually, eye gaze is kind of like pointing with your eyes, which is a very easy way for us to adapt our gesture model and apply it to eye gaze. So that comes out pretty out of the box. And on the other side, the robot no longer has to point. It can actually highlight things or even show its probability distribution of its uncertainty, which wasn't even possible before. How do you explain a probability distribution using language? Not very easy. And so what we did was we added these two things in, and it expanded our fetch POM-BP to have mixed reality as a bidirectional communication interface. And so this expansion of the fetch POM-BP with mixed reality is what we call the physio-virtual Dijkstra's PVD, or the PVD POM-BP. And so you'll see an example here from the perspective of a user wearing the mixed reality headset is actually looking at the world, and they can say and point something like, can I have that glass? And now the robot can just highlight that using its headset rather than pointing. And you'll notice that the eye gaze tracking you'll see here as a little green dot tracking where the user is looking is pretty highly accurate, which makes a lot of sense compared to the gesture tracking, because the headset's right on the person's eyes, so it's easy to see. Whereas the Connect, which is on the robot, is very far away from the human. So what I want to emphasize here is mixed reality is a really natural platform for facilitating multimodal human-robot interaction, because it has all these sensors on it and even allows you to get more than you could before. So this was a really cool example where we had developed a really nice model for intelligent question asking. And after we had developed all this nice mixed reality robot middleware, we were able to throw it into the mix and get huge improvements over the original Fetch POM-BP. Both because the beliefs were already getting updated better due to the eye gaze, and we were able to ask more effective questions using virtual pointing instead. So if you're interested in multimodal human-robot interaction, especially at this kind of high-level control with like intent inference, I think mixed reality is a very natural and amazing platform for that. So to summarize, we went through what the mixed reality robot middleware is and how to start getting going with it. And I went through 3 different levels of hierarchy for control that you can do with mixed reality. And one thing I'd like to emphasize is that there wasn't really much learning going on here, but a lot of what my current work is actually integrating learning into the loop here. I'm very interested in getting robots to be autonomous, but also learn from humans in order to be autonomous more efficiently. So if you're interested in this question of how could we get more learning in the loop, I'd be happy to talk about that. That's a lot of my current work. But anyways, I want to end with some final takeaways that I emphasized here. So what is VMHRI? Important thing to me, mixed reality is a very catch-all term, and virtual reality is really useful for remote HRI. Augmented reality is really useful for in-person human-robot interaction. I want to emphasize too that if you think this technology is cool, it's very commercially cheap today, and if you want to try it, play with some Unity, try out Raw Sharp. Give it an hour. It's a lot of fun, and it's really cool what you can do with it. And lastly, I hope I got to show a little bit of examples of what you can actually do with VMHRI at varying levels of control, whether that's very fine-grained teleoperation, slightly higher level visual programming information, or even very high level interfacing with natural modalities that humans like to use. So that's the end of this talk, and I just want to thank all my amazing collaborators that I've gotten to work with over the years. I could not have done this alone, and it's been a lot of fun. So I'll leave it at that. Thank you. And if you have any questions or want to talk or want to see how you can get this technology into your own work, I really would love to talk about that. I think it's really cool and exciting. So thank you so much for having me, and I'd be happy to answer any questions.
Yeah, what questions do people have? I obviously have a few, but Lauren?
I'm curious, the idea of if you don't have a headset available, and if you had like a phone that have you ever like looked into, for example, we do some in-home like scalable robotics, and I know that we have kind of a few projects where scalability is a goal. And I'm curious for kind of in-home scalable deployments, and lots of people have phones, like how do you feel this type of work could transfer using like a phone instead of a headset?
Yeah, so I think there's a lot of things that you can do with the phone. So to emphasize, I probably should have included a picture of that here, but on this slide, there's something like the Google Cardboard, which is like a very simple cardboard thing that you can turn a smartphone into a virtual reality headset. That's extremely cheap. And then on the augmented reality side, yeah, your phone is pretty much an AR tablet, right? And you can just go a little bigger if you want with a bigger one. So I think those are powerful and are good visual interfaces, but I think they miss a few things, at least that I think are directly relevant to control. So first off, if you remember what I said about here with like mixed reality, one thing that I really like about it is that you get eye gaze. And I think that's a really powerful modality that is a little missed out on with something like a phone, but maybe isn't that important if you're going to be emphasizing something more like mid-level programming anyways. So I think for something like that, it's very powerful. But also when you're holding a phone, you can't really use your hand gestures as effectively. And also it has limited situational awareness because you have to look at the screen and that only has a limited scope. Whereas mixed reality headsets still have a limited field of view today. So if you put it on, you'll actually be a little more surprised than when you see the cool marketing videos, but they're still expanding. But that is maybe not as important when you're not working in safety critical situations. But I would argue that if you are working close with a robot, you may want to actually have not be looking at a screen. But outside of that, yes, I think tablets or phone-based technology is very relevant. The Ross Reality Toolkit and, for example, like Ross Sharper, there's another one called iVis. These are all, they can be reused and optimized for those platforms. From the perspective of Unity, which is the game engine that's actually developing these that's used to facilitate these virtual environments, they can be deployed to various things like iOS or some other platform. So it's the nice thing that I really like is how plug and play all this technology is. But one thing that I have a lot of respect for, which is what sounds like a lot of all of your works, is that you guys work with a lot of you have specific groups that you're trying to target and work with, and you have much more constraints. So I think thinking about how the grandiose ideas that I'm presenting here and that are assuming maybe these more cumbersome or expensive technologies could be translated to smaller applications or cheaper things and opportunities like things on the phone. I think there's a lot of parallels there. Yeah, I think that's a really exciting thing too. But from my perspective with the control, I think there's a lot of things you get out from actually getting the headset right on the head, but still very cool. And I like that technology a lot.
Thanks, Eric.
Just to actually add to that, because we are currently moving to iOS and Android at this very moment today. What do you think for intent recognition in the idea that you can use the center of the tablet as quote unquote eye gaze, right? Like a proxy. And then because you have head pose, right? The tablet plane perpendicular to it is head pose. And then you also have manipulation because you still like grab things. And now there's like a fast Unity plugin to do hand tracking and grab things. So you can put your hand in front of the tablet and grab things, which I haven't tried yet, but I just linked in the thing.
You know what's really, I'd like to see some more investigation about that with respect to what you just said, which is that like you could treat as where you point the tablet as eye gaze. One thing that we found that was really bad about using eye gaze in our case is the following. If you want to ask, let's say that you have this situation where the robot is like, do you want this one, right? So what the way our observation model works is if you point, we believe you want objects that you're kind of pointing towards more likely. And if you use words that describe those objects, they become more likely. So normally humans use language to describe objects they want, and normally they point at things they want. But the problem with eye gaze is you don't just look to communicate, you look because you literally need to look around the environment and see what's going on. So eye gaze plays a dual role as a sensor for the human and as a communication modality. And so we actually had issues where the robot would maybe say, do you want this one? And would point at a wrong object. And so the human would look at that object, and then by looking at it, the robot would slowly become a little more certain about that object until the human said no, and then it died out because we really take no's and yeses and those kind of words like confirmations as very powerful. So what you're saying is maybe it'd be interesting because if you were holding a tablet and you might not just point at things that you're looking at, but if you wanted to maybe have the robot as a communication channel, you'd point it to kind of know that like, this is the eye of the robot. So like I can look at things, but then when I want the robot to know what I'm referring to, I just point at it. that actually gets around that issue very easily, but may have some of its own issues with like holding the tablet. So overall, from an eye gaze perspective, not only do I think that solution you said would like be a good proxy, but I think it actually even potentially, though this is unfounded, I haven't seen any studies on it, would get around this communication sensing problem that eye gaze has. And I'm very interested in this problem because I think eye gaze is very powerful, but it's interesting how it plays a dual role. But that's a good question. And yeah, I think that would be viable. I'd be very interested to see that. Yeah, that seems like an interesting thing. Once again, though, like if you were actually, we haven't done any studies with this yet, but I'm very excited to do more studies where we actually have the human and the robot collaborating together. That would involve maybe doing handoff things. And that might be a little more difficult for the human to actually hold a tablet. But once again, I think that makes a lot of sense and is a really good platform.
Brandon, you have a question?
Hi, so thank you so much for presenting. I definitely learned a bunch. Also, I love that there is just so much like visual stuff in this, makes it a lot easier to follow. So I guess this question is very, very broad, but where do you think the VAM HRI field will be in like 5 years? And how do you think this will kind of like trickle down to more like consumer / lay person applications? Because I guess even like the learning curve for like Ross, and I'm sure Ross Sharp is maybe easy-ish for us, but obviously not easy to someone who doesn't know how to code at all.
Yeah, so that's a really good question. To just start, where I think, I mean, like if I had to make a prediction about where I think VAM-HRI will be in 5 years, one thing I continue to see is that VR and especially AR technology will get cheaper. And as it's cheaper, I think more labs will start to adopt this technology, whether it's in the form of like having more tablets or having an AR or VR headset. I really think this will be something that if you were starting your robot kind of lab, this would be something like you'd want to buy with a microphone and with like a controller. So I think we'll start to see this technology be much more common in labs. So that's one thing. Along with what you said about, yes, like things like Ross, for me, Ross is really difficult. Like, I mean, like it's nice on one end, but there's a lot of things. But this is just because like robotics is very difficult. And to make a middleware that abstracts away all the complications of hardware and networking so that it's easy for people, I think to me is probably always going to be a challenge. And I don't know if virtual reality or augmented reality are necessarily something that's going to rectify that. But what I do see is if what I hope is that something like Unity or other game engines become extremely integrated with things like ROS, because they're extremely powerful engines to develop virtual environments. And even things like Unity, they're investing huge amounts of money into robotics themselves. So like maybe in 5 years, I won't be recommended something that's like from a third party. I think we'll just be using Unity's ROS like connection. And what I think that we'll see is we'll see a lot more connectivity between the amazing API tutorials and ways that it's easy to just start. If you want to make a video game today, a 3D video game with Unity, it takes you an hour. It's you literally go into the it's so amazing. Like similar to how I think the gaming community pushed deep learning through the hardware of GPUs. And that really made this technology very readily available to use for deep learning. I could see things where these technologies and interfaces for MR and VR from video games make it easier for us to integrate and get people started from a robotics perspective. And actually, myself, I've played a lot of virtual reality games and gotten ideas from them into literally developed exactly what we did into these interfaces. So I also really hope there's a much more cross collaboration going on between people who work in maybe in game development and how we can use that for robotic interactions. I think that's another really exciting area. Yeah, does that answer your question?
For sure. Thank you so much.
Great.
Yeah, I have a quick question related to learning. So I have been reading some interactive RL paper, and one of the tamer paper, like I think in the demo, in order to like communicate rewards, they use a clicker. and it's a very inefficient way to communicate rewards. I'm wondering, like, how do you think them HR, like virtual, mixed reality can be a little bit more efficient to communicate something like that? Or like, what's your vision in terms of like combining mixed reality with RL?
Great question. So let's talk about it from the two ways, right? Because like in a human robot interaction, you have the human to the robot, and the robot to the human. And one thing that you were just asking about is from more on the side of the human to the robot with something like Tamer giving rewards as a clicker value. But actually, if you don't mind, I'm firstly going to say what I think is really interesting from the robot to the human, because that's a very important part for learning. So if you think about from a reinforcement learning, when you specify reward information, we would say that's policy independent, because it's the reward function is the reward function. It's the reward function. You're getting samples from it. But sometimes I give feedback that's policy dependent, like dependent on what I think the model of the robot is, I give different feedback. And so what this means is that in order for a robot to learn from a human, it's really important that the human has a good model of the robot. And so I think this technology is unbelievably useful for actually making the human understand the mental state of the robot. So here I had said previously that in our fetch POM-DP, the robot has this belief distribution of objects, but that was hidden from the human. The robot just has that in its head. But with virtual reality, you can literally show that over the objects. And we didn't show it in this paper, but when we did that, the humans would just start producing observations that were useful, because they're like, oh, you're uncertain about that? I'll just clear it up for you without even asking a question. And so like, if you just showed belief distributions, humans naturally start producing more useful observations. And so like, it kind of showed that it was almost hurtful, because it was like the robot didn't need to ask questions. Like the human would just resolve the ambiguity very effectively. So I think there's a huge amount of power from a teaching perspective where the human, in order for the human to give good teaching feedback, they need to have an accurate model of the robot model. Well, something like Tamer doesn't necessarily depend on that because it's reward-based. There are many other kinds of feedback, like the sampling from the advantage function, for example, that really do depend on that information. Now, to answer your other question, which I think, or your main question, which is maybe from the human to the robot, I get very excited about that at the mid-level programming level of things. So I had emphasized in this previous middle level where we were building plannable representations, but there's a huge amount of information that the human can supply. And if you look at these things, if you're familiar with the notion of a semantic map, this is essentially all the information that you'd really want in a semantic map that would facilitate task planning. So there's so many different, like, how would you communicate the pose of an object to a robot? That's really hard. What am I gonna, like, I don't even know I don't know where the origin of the map is, and I don't know how to specify quaternions or like roll pitch. Very, very difficult. So there are so many state pieces of abstractions. I think at the level of abstractions, I guess, at this question, like rather than like only being able to give reward information, what happens if I want to give state information? Or what happens if I want to give action information? Like, how do you manipulate an object such as to move your arm to open up a revolute joint? Is very hard to explain with language. And if I put my hand, like, and if I don't want to maybe grab the robot because now my hand is in the middle of the visual data, so now it's corrupting it because you're seeing me grab you, it's not very easy. So I think at the level of it's more expressive in what kind of things you can communicate. And my general takeaway is that language is very powerful for communicating topological or semantic information, but it's very bad for communicating metric information. So distances is very hard for me to like communicate that. But with mixed reality, I can specify geometric or metric information very easily. Like it's very easy for me to take a virtual object and align it over the real object and pose it. And so when giving feedback, whether it's maybe higher level feedback, I think natural language is very good. But if we want to communicate very potentially geometric information about the world and teach the robot about that, which is very important for control, I think mixed reality technologies and visual interfaces are amazing. And so a lot of my work in reinforcement learning is exploring how to have robots autonomously build state and action abstractions so as to facilitate task planning and hook in mixed reality so that the human can see those abstractions, augment them, and improve them. But that might be a little high level, and I'd be happy to talk about more of my current work in that area offline or something.
Yeah, that's really interesting. And I really like how you define the problem from the human to robot and from the robot to human. And yeah, that really makes things a lot clearer. Thank you.
Great. Yeah, thank you so much. I appreciate that. I'll go to...
Any other questions? I have one more, but I'm going to wait until everyone else is done. I have kind of an odd question. So you do this VanimHRI, right? You have essentially just a sensor on someone's head, which is great, amazing. You have tons of sensing and a ton of assumptions you can make because the damn thing's on their head, right? What do you think of the idea of modeling some like human intent or something where, you know, the feature space is all these sensors that are both internal to that headset and external? So, you know, your Baxter Connect camera or whatever. And then you try and do some sort of transfer over to where you drop out the headset and do some intermediary prior features using the prior, like you collect with the headset and the external stuff, then you drop the headset and you try and get the same performance with just the external stuff and essentially use the headset as some sort of like, you build some sort of intermediary feature model sort of thing. Does that make sense?
Yes, so maybe just clarify and tell me if this is what you're intending. So the headset itself is a kind of like a robot that has very little actuation capability. And so there's a lot of overlap between what the robots in the scene are trying to do and maybe what your headset is trying to do. Maybe that's like, and so maybe they're both trying to build a metric map of their environment. And so there's some overlap there, but they're posed in different parts of the environment and you might take off the headset. And so like, it's not going to be building a really good map, but the robot's still moving around. So how to go back and forth? Are you talking?
Well, I'm actually talking from the human intent. So you're trying to model some human intent or something, right? So essentially you have these inputs into your model when the headset's on a person. And theoretically you could learn some sort of prior, right? That uses those as some form of almost label into a non-headset version of an algorithm, right? So you have an algorithm trying to figure out what the heck they're looking at. Does that make sense? I don't know if you can do that. That's just like an idea. Like basically drop out use those green arrows to learn something intermediary and then drop out the green arrows.
Yeah,
right?
Yeah, so to be clear, if you have these lack of green arrows, it's the fetch POMDP, which requires no mixed reality headset. If you have a mixed reality headset, you add in these two extra, like an observation, you add additional things to your observation model and you expand your action set. And then you get the PVD POMDP. And so if the person just takes off the headset, you can switch to the fetch. And if they put it back on, you can switch to PVD. And there's like the belief distribution carries over.
Is there any way you could transfer things you learn and model from like prior PDP onto the fetch? Does that make sense? Like,
yes, so that's what we actually, so maybe this is kind of getting into our building plannable representations paper that I mentioned before. But what a human can do is in a training environment, use mixed reality to teach the robot some information about how objects, what is a light switch? It's a kinematically constrained knob. And if I want to affect that knob, you grab the knob here and you move the little knob downward. And now I taught that with mixed reality, but it is in some sort of language and state representation that the robot understands, so that if I put it into a new environment and it perceives by like doing some sort of perceptual tracking, matching the model that I had taught it to that object, it can then transfer that knowledge and I don't have to be wearing the headset at all. So this is kind of about like maybe using mixed reality to interface and teach the robot and learn, but then that's not tied to just the mixed reality headset. It's actually concrete information that the robot can use and ground to the real environment so it can work autonomously. So that was exactly what we had done a little bit in this work. Is that what you were asking about or something?
Yeah. So yeah, this is like a straight LFD to some degree, right? LFD-ish sort of problem. And this is intentional LFD from the person. I'm thinking, what if you could do the unintentional stuff? But it's just some idea I had when I was looking at your stuff, you know, because like eye gaze is unintentional stuff you're learning model stuff with. I mean, it's an hour, so it's something that actually I kind of want to think about and flesh out.
I'd be happy to talk about that more. None of the works that I'm discussing here, or to very limited extent, they're doing model learning. It's very limited, very little. And more of my current work is actually in the side of doing model learning and also model-free learning for policy search and like implementing that. But yeah, I'd be happy to talk about, it sounds like a really cool idea. I'd love to talk about that more offline too.
Yeah. Thank you, Eric. It is 11, our time, obviously not your time. If you have to go head out, do you have actually any questions for us or anything? Obviously, anyone who has to go, you can head out too. Because I know you had some stuff. Or you said you had a question or two for people.
Yeah, no, well, I don't know if I have any general questions for the group, but I wrote down everything that I had learned about everyone in like the minute or two sentence. So like, I'd love to talk with I have time still to be here afterwards, but if everyone has to go and if anyone would be happy, maybe talking via email or having a conversation to more depth, I have some questions I have about various independent certain research. So maybe I'd love to talk with people individually about their projects, and I have some questions because we bring, I'll just emphasize that all these works, like I said, behind the scenes, we did a lot of user studies, but they were all with just students that we had grabbed off of Brown campus and had come in. And yeah, we had huge numbers of them, but I mean, what I've really lacked in my own research is going out into the real world and working with target populations and actually getting this going with them. So I think just from the array of things I heard, there's a lot of cool applications, and I would love to brainstorm and think about how these technologies could be very easily integrated and possibly used to improve those situations. I'm just curious about, I just like thinking about that. So I really should have left maybe a slide on my email here or something so that people can message me if they want. But I would love to have just conversations and learn more about what work everyone is doing. And if you want to reach out and have a conversation someday or something, please do that, because I would love that. But yeah, I don't know if I have anything generic to ask, though I appreciate that.
Additionally, Eric, this is only our second we have usually these meetings, but we'd been discussing our own work, our papers that we'd read. This is our second one with a guest speaker. So if you have any feedback for us, you can either, let us know, share it with Tom. I hope, we definitely all really enjoyed it, and we hope you did too. But if you have any feedback kind of about the structure of the meeting, student to student, we'd love to hear it.
Yeah, so actually, I'll say, because at Brown, we on Fridays, we run weekly kind of meetings like this for an hour, but instead of it is kind of about our work, but also we have a lot of guests come in. I'll say one thing I really liked at the beginning was the popcorn kind of thing where everyone ran around and gave me a little information. We don't do that, and honestly, I think we should, because like that was really nice and good. Otherwise, for some feedback, you guys were a great audience, and I appreciate that. If anything, I'd love to have more time to talk with you all individually or just like in a group and just have a more casual conversation about learning what your research is. Yeah, I would love that, if anything. So that's the only thing I would give feedback on. But otherwise, this was a really cool, great meeting, and I really appreciate getting to be here and speak with you all.
Thanks, Eric. We really appreciate having you. Thanks for your time as well.
Yep. Thanks, Eric. We can probably close the meeting then. And I'll stop the recording.